linear down to zero. We did something similar with gravitation, gravitational force. If you'd like, we can go through the derivation in 5 minutes, if you'd like, or if anyone would like. Or you're just trusting that I'm not making a mistake here.
I want to see that.
You want it? All right, there we go. Someone who doesn't believe that I did it right. I know the electric field inside a conductor is zero when all the charges on the outside. So any charges outside of where I'm talking about, I'm going to ignore. I'm not going to do that derivation right now because that's 45 minutes. So when I am here, and we can go for that typically stunning visual effect. So if I am within this ring right here, I'm going to ignore all the charges outside of it, because their contribution should be zero to the electric field inside here. So if this is some distance r, if we have a uniform charge distribution, that's equal to the charge divided by the volume. It should be proportional. No matter what section I take, this ratio should be the same. And so for the entire thing, we have Q over 4/3 pi r cubed, where big R is the radius of the entire dielectric. And that should be equal to, I'm going to just call this Q inside, over 4/3 pi r cubed. And this would be the charge that's within our smaller section. So my electric field should be KQ over R, over R squared, R hat, for R greater than or equal to big R. But if I'm less than that, my charge here is not the charge of the entire thing, but the charge of whatever internal sphere I'm looking at. So this would be KQ sub I over R squared, R hat, for R less than the radius of the dielectric. Okay, dramatic pause for questions. Well, I know from this ratio over here, big Q sub I is equal to, well, we just solve for that. The 4/3 pi go away nicely. And I'm left with big Q little r cubed over big R cubed. I plug that into here. So I have K big Q little r cubed over big R cubed over R squared. And so what I'm left with is the electric field inside the dielectric with a uniform charge distribution is K times the overall charge over big R cubed times how far I am away from the center. So it's a linear relationship, R hat. So it's a linear relationship for the electric field once I'm inside the sphere. That's where that comes from. So the electric potential I know if I'm outside the spherically symmetric charge here, then I'm just going to be a KQ over R. Where this value right here is K big Q over big R. And this value right here would be K big Q over R squared, so big R squared. So the question is, what happens after that? If it was the conductor with all the charge on the outside, this just flatlines. But we still have some charge inside here, and so I know that since we're only dealing with one variable here of radius, so this would be the negative dV dr. In other words, my electric field is the negative slope of my potential here, which means this linear graph here is that is the negative slope of this. Well, this slope is positive, or sorry, these values are all positive. So my slope is going to be negative. I know that at this point when my electric field is 0, my slope here is 0. So I know it's going to be flatlined either there or something like that. Because we have a nice smooth transition here as we start moving in, we aren't going to have any sharp points. It is differential the entire way, but since the slope needs to be negative the entire time, if I suddenly drop down here, I have a positive slope. So I have a negative slope here. And it's going to sort of curve like that. Notice that as I progress this way, my slope becomes more negative. So this becomes a larger negative value, which means my electric field becomes a larger value, which it does right here. The other way of looking at it is that my potential is a negative integral E dr, technically E dot dr. But electric field is in the same direction as my radial there, so negative integral of E dr from infinity to 0, sort of working my way that way. So when I get to here, my integral, my area under the curve is increasing, but it increases at a slower and slower rate as I go that way. So it increases, but then at a slower and slower rate. I assume if you didn't have your mask on, your jaws would all be dropped at just amazement of this stuff. So I'll just go with that. As opposed to drool sort of dripping down the side sort of thing. Other questions on this? So Daniel, well, now that it's over, are you glad you asked about that?
Yeah.
Okay, all right. Other questions?
For the test, when the question is about the rod or the infinite plane, do we have to derive it each time, or can we just memorize?
You can just memorize it and go for it. In theory, you've already memorized it.
Will you give us like the volume of a sphere, area of a sphere, things like that?
If you need it. I can't remember if it's traditionally at it's part of the equations, but if not, then I'll be glad to give it to you. Or, with all the extra time you have, you can just derive it. We've all had how to. Just do a triple integral. It works. All right. Just from a cataloging point of view.